All right, so the next piece, we are going to start doing a lot of graphs of functions and their derivatives, and that's really going to take us probably the next month to get through all the aspects that we're looking at. So today, we're just going to talk about something that we actually have seen before, the difference between local and absolute maxes and mins. Remember, we did talk about those like in pre-calc, college algebra, so you have heard those words before. And we'll talk about how we can find those from the equation of a function so that we know where they occur on a graph. So kind of the motivation here, some of the things this helps us find. We've done some of this already, but this idea is used a lot in optimization. If you're finding a maximum or a minimum, you're finding the highest or lowest of something. So you might want to find the shape of a can that minimizes your manufacturing costs. Or you want the maximum acceleration of something. Or, even a medical aspect, what's the radius of a contracted windpipe that expels air most rapidly during a cough? What angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? This is kind of why calculus is not just a math class, but if you're going into a science field or a business field, you have to have your calculus, and a lot of it has to do with the maximization. If you want to maximize your profit, but minimize your costs, those types of things. We're going to start off pretty basic, just looking at graphs. An absolute max is the highest y value our graph hits. The absolute min is the lowest y value it hits. If it hits that same high point more than once, you could have two absolute maxes or absolute mins if they were exactly the same. But you may not have one. We talked about, I think in college algebra, I would give you a graph like this. Does that have an absolute max? No, because it keeps going up forever. Does it have an absolute min? No. So we don't have to have them, but we might. Terminology, we can say f of 3 equals 5 is the absolute max. That just means when the x is 3, the y is 5. F of 6 equals negative 2 is the absolute min on this graph. In other words, sometimes instead of absolute, you might hear global max or min. It means the same thing. If I just ask you to find extreme values, that's just maximums and minimums. So extreme values are everything together, maxes and mins. Tell me which is which. Then we have local maxes and mins. Local maxes and mins don't have to be the highest or lowest on the entire graph, just higher than the surrounding points, higher than the points on either side of it. When we are looking at these, so here's an example. This point right here, is it the highest on the entire graph? No, but is it higher than the points on both the left and the right? Yes, so that's what we call a local max. It's the maximum in that area, but not everywhere. What would this one be? Okay, this point right here, it's the highest on the graph, so it's the absolute max. But it's also higher than the points on either side, so that is both the absolute and the local max. We can have many local maxes and mins. What would I call this point? It's a local min, but the graph does get lower over here, so it's just a local. Now, one thing, your local max and min can't be endpoints. Because if I look at this one, it's higher than the points on the left, but are there any points on the right to compare it to? No. It could still be an absolute, but is this one an absolute max or min? No. So this point is nothing. What would this one over here be? The absolute min. It can't count as a local min because there's no points to the left, but there are points to the right. So absolute maxes and mins could be endpoints, locals cannot. And a point could be both local and absolute. All right. Let's go this way. What are the maximum and minimum values of x squared? We know what x squared looks like, don't we? What is it? Parabola. 0 squared is 0. 1 squared is 1. Negative 1 squared is 1. Okay, so what are my maxes or mins on this? You can write it like, I don't care if you give me an ordered pair. A lot of times I will write it in function notation and 0, 0. I don't care which way you do it. So ordered pair is fine, or you can do the function notation. Is it local or absolute? Or both? Both. Local and absolute min. There are no max in this. No local or absolute maximums on this one, because both ends are going up. What about x cubed? What's x cubed look like? Cubed is 0, 1. Yeah. All right, what about this one? Maximums, minimums? No. So we don't have to have them. Then I apologize, I tried to put a graph on here, but it did not print very well, so it's kind of hard to read. So this is an open circle right here. You know what color I need to make it so we can. This is a closed circle, this was an open circle. I apologize for how difficult that is to read on your paper. All maxes and mins. So let's just start with our absolute. Absolute max. What is the highest point on this entire graph? You can write it as an ordered pair if you did function notation, f of 4 equals 3, either way. So this point right here is the absolute highest. The absolute min, the absolute lowest. The lowest my graph ever hits is down here. But what kind of circle is that? Open. So is that an actual point on my graph? No. So do we have an absolute min? I can't tell you the closest point to that. You could always get closer. So if it's an open circle, there just is none. Local max. I'm looking for points other than endpoints that are higher than the points on both sides. Okay, so this one is higher, but what kind of circle is that? Open, so that wouldn't count. This one right here, there's a break in my graph, but does the graph exist on both the left and the right of that point? Here's to the left, this is to the right. So it does exist in both sides. Is this higher than both of them? It is. So it doesn't have to be continuous there. The graph just has to exist on the other side. So that is a local max. Keep looking. This one, it was higher than the points to the left, but on the right, those are higher, so that wouldn't work. My other local max is my absolute max. F of 4 equals my local mins, these are lower than the points on either side. Okay, can I count this one? No, for several reasons. It's an endpoint, it's also an open circle. Can you tell me any local mins on here? Okay. Keep going, this was a max. This one's an open circle, so it can't count as anything. Open circle, so it doesn't count. This one, it's lower than the points on that side, but not this side, so it can't count. The endpoint can't count. But there is actually one other local min on this graph. Anyone figure out where it might be? Yeah. This point right here. It's a closed circle, so it can count. The points on both the left and the right are higher than it. So it is lower than the points on either side. So we have to kind of adjust our mindset. It doesn't have to be continuous to be a local max or min. The graph just has to continue on for it to count. All right, questions there? If I asked you to draw a graph that meets all these expectations, an absolute max at 5. Okay, I should be more clear here. I mean, when x is 5. So when x is 5, I have a high point on my graph. An absolute min at 2. So when x is 2, I have my lowest point on this graph. A local max at 3. Local mins at 2 and 4. Okay, so my lowest x is 2, my highest is 5. Can 2 be an endpoint on this graph? Could it be my starting point? No, because I said it's a local min as well, so it has to exist on both sides. Now, I can't just draw an arrow going up forever because this has to be the highest my graph ever gets. So maybe I'm just going to start it here. Okay. This has to be the lowest, we have to continue. At 3, I need a local max. Right? It doesn't have to go up very high. Just saying when I get to 3, it's got to come back down for a minute. I have a local min at 2. 4 has to be a local min, so I have to come back down. 4 go up. And 5 has to be an absolute max. Could 5 be the endpoint? Yes, absolute maxes can be endpoints, locals cannot. Is that the only graph that would work? Absolutely not. I just said draw a graph that met those requirements. Any questions so far? Do we understand what local maxes and mins are? So these can be found using some different calculus ideas. First thing is if you have a continuous function on a closed interval. So closed interval tells me we have end and or enclosed circles. They're not open ones. Then it has to have an absolute max and min in that interval. Okay, and I put some graphs just to show you that. If you have a continuous function and we're only going from A to B, you have to have a highest and lowest point because I said it ended at those points, so it can't keep going up or down. If it's continuous, there's no breaks in the graph, so we have to have them. Now that only works if your graph is continuous and closed. If it's not continuous, you know, we could have something like that, and this one doesn't have an absolute max because there's an open circle. If I look at this one. It's not a closed interval because it never has a point when x is equal to 2. It's a vertical asymptote, keeps going to infinity. So it's only true under those conditions. If we have those conditions, though, we should be able to find the maximum and minimum. How? Look at this graph. My absolute max is at C, my absolute min is at D. How could I find those? What's happening at both of those points? Yes. I drew in those tangent lines. The slope of those tangent lines is 0. How do we find the slope of a tangent line? Derivative. So I'm looking for when the derivative is 0. Okay, haven't we kind of done that already when we were like finding the maximum height of something? What did we do? We found the velocity and set it equal to 0. So we've kind of already done that. But it will work in all of these cases. So that is the first rule. If you have a local max or min and the derivative exists, it's going to be 0. Now, the question is, if the derivative is 0, does it have to be a maximum or minimum? So if we think about x cubed, the derivative is 3x squared. If I set that equal to 0, x squared equals 0, so x is 0. So at 0, we have a horizontal tangent line. Do I have a maximum or minimum at 0? No. So the maximum happens when the derivative is 0, but just because the derivative is 0 does not mean it has to be a maximum or minimum. It means it could be. All right. I want to look at one other case. Absolute value function. Can we agree this is both a local and an absolute min? Yeah. But that's not a place where the derivative is 0. We've talked about this before. When we think about the absolute value, we always did a piecewise function, right? We said if you put in a positive, you get out the positive. Oops. And if you put in a negative, you get the opposite of what you put in. And when you do the derivative of that, the derivative of x is 1. Derivative of opposite of x is negative 1. Okay. 0 could technically fit into either of those categories, right? The absolute value of 0 is 0. When we look at this, at 0, my derivative is equal to 2 different things. So the derivative does not exist at 0. And we've talked about it before with corners. I always said the derivative doesn't exist there because there wasn't a unique tangent line we could draw if it had a sharp corner. So places that we didn't have derivatives were vertical tangent lines, corners, breaks in our graph. But it's still a maximum or minimum. So what we're seeing is we have a maximum or minimum if the derivative is 0 or doesn't exist. Those points are called critical numbers. So critical numbers are any numbers where the derivative is either 0 or does not exist. And those are the places that could be maximums or minimums. So for example, if I asked you to find the critical numbers, we need the derivative. What would you do before you did the derivative of this? I mean, we could do product rule, but I probably wouldn't. Would you guys just jump in and do product rule? I would probably distribute first. Okay, this is like x to the first, so that's 5/5, so 8/5. So the derivative, exponent comes down, so 4 times 3/5, 12/5, x, subtract 1 from the power, so -2/5, minus 8/5, x to the 3/5. Okay, the critical numbers are anywhere this is equal to 0 or undefined. So let's set it equal to 0. If I do this, the x would come down. Since it's a negative power, I could add that one over. So I just rewrote it without the negative exponent, added my second term to the other side. What would you do now? When you add those, 5/5 is 1. Divide by 40, so 60/40, 6/4 would be 3/2. So my critical numbers, x is 3/2. Okay, that's when the derivative is 0. Is there anywhere this is undefined? Think about that negative and put it on the bottom. What can never happen on the bottom of a fraction? 0. What would make this equal 0? 0. So it's undefined at x equals 0, so that's actually a critical number as well. A lot of times you might see it called critical number. A lot of times I'll call it critical point as well. So you might see me label it as CP for critical point, or you can do critical number. I don't care. Those are kind of interchangeable. So critical points, we had to find out when the derivative was 0 and then check if it was undefined anywhere. All right, let's do another one. I am going to skip this slide for just a second, and I want to go here to actually find the absolute max and min. First thing, maxes and mins can happen at critical points. So we have to find our critical points. How do we find critical points? Critical points are the derivative. We need to do our derivative. So that would be 3x squared minus 6x. Derivative of 1 is 0. And I need to find out where this derivative is 0. So I might look at this and take out a 3x. So I get x to be 0 and 2. Is there anywhere this is undefined? No, there's no radicals, no negative exponents, just polynomials, so that's fine. So my critical points are 0 and 4. Those, or sorry, 0 and 2. Those aren't guaranteed to be maxes and mins, it's where they could happen. Now this problem does ask me to actually find them. So this is the step we're going to use to find them. First we find our critical points, then we're going to find the y values for the critical points and our endpoints. So I am going to plug my endpoints and my critical points into this function and see what y value we have. All of these, I need the points on the actual graph, so I'm going back to the original function and putting them in. So grab a calculator if you need to. Let's plug these things in. Put in -1/2. So when I put in -1/2, I got 1/8. When I put in 0, I got 1. 2 gave me -3, and 4 gave me 17. All right, so can you look at this and tell me which one's my absolute max? 17 is my absolute max. Which one's my absolute min? So f of 4 equals 17 is my absolute max. F of 2 equals -3 is my absolute min. So we basically find our critical points, plug those and the endpoints into the original. Any questions there? This is where I'm stopping for today. The assignment is pretty short and sweet today. If you look on Google Classroom, there's a handout with 6 questions. The first 4 are just looking at the graphs and telling absolute and local maxes and mins. The last 2, you are finding the critical points only. You're not actually finding the maxes and mins. And we'll continue with this tomorrow.